No Entrevistando Cientistas, convidamos o professor, pesquisador e influente no campo de oncologia Dr. Lorenzo Galluzzi. Tendo concluído seu bacharelado e mestrado na Università di Modena e Reggio Emilia, e seu doutorado em Université Paris Sud, Dr. Galluzzi atuou em diversas instituições na Europa e nos Estados Unidos, como o Gustave Roussy Comprehensive Cancer Center e Cornell University, até sua filiação mais recente como Associate Professor na Fox Chase Cancer Center. Dito isso, perguntamos: Dr. Lorenzo, você foi entrevistado para essa disciplina em 2020. Para aqueles que não assistiram, você poderia nos contar um pouco mais sobre você e o que mudou na sua vida e carreira desde 2020?
So I moved out of chemo and really focused on radiotherapy and immunotherapy. And also initially I had some sort of larger approach, and I moved in and I started focusing on mostly breast cancer. So I refocused a little bit my activity. And that's when I was interviewed last. In the meantime, obviously we had COVID, things have changed. I mean, along that time, the lab has started to expand. We ended up having like a mid team of like 8 to 10 people. Then we got COVID, things got a little bit complicated, but we were good enough to be able to publish our foundational papers and also to start getting federal funds from the US, which is a very a turning point in the academic career of a US-based investigator. Until you get NIH or DoD-based funds, it is complicated to establish yourself. And after 7.5 very productive years at Cornell, I moved to Philadelphia, where I am based now. At the same time, I got promoted from assistant professor to associate professor, which is the next logical step in the events of a PI in the US. Now my team, obviously, we moved in October last year, so my team went through a little bit of a bottleneck, but we are re-expanding. We are already 7, and I would estimate that by the end of the year, we're going to be around 10 or 11 or something like that. So back to a normal size for my lab, and I think the cap size of my lab.
Dr. Lorenzo, em uma das suas publicações, você propôs o conceito dos 3 Cs, camuflagem, coerção e citoproteção, como forma de sistematizar os principais mecanismos de evasão imune do câncer. Você poderia explicar como esse modelo surgiu da compreensão dos 3 Es, da imunoedição do câncer?
Yes, I think we were inspired. So the 3Es is a model through which that postulates that malignant cells need to evade the recognition by the immune system, which initially is capable, first of all, of eliminating them, and at some stage at keeping them under some sort of dynamic equilibrium whereby there's local proliferation of cancer cells, but they cannot go anywhere else because the immune system kind of contains them there. So they're still not a real problem from the patient. This local proliferation, though, enables the acquisition of different or extra genetic or epigenetic defects that might randomly attribute one of these cancer cells or few of these cancer cells with an advantage against the immune system. And that has been previously framed under the evasion of the triple E paradigm, thanks to Bob Schreiber. This is a very classical model of the cancer immune system interaction. And when we thought about evasion, obviously the literature is very abundant there, because evasion is a problem for all therapeutics. It's a problem for immunotherapy, but it's also a problem from chemotherapy and radiotherapy, because now we know when these therapies are successful, they still operate to some degree, at least partially, by engaging an immune response. So if cancer cells are no longer capable of being recognized by the immune system, even chemotherapy might not be as efficient as if cancer cells are being seen and eliminated by immune cells. So we started thinking about like, how can we provide an interpretation of all these mechanisms? Because the mechanisms, like specifically, there's dozens, perhaps even hundreds of them. There are different molecules at play, there are different strategies at play, but we wanted to provide an understanding that would go beyond the individual specific pathways to just figure out like a conceptual framework. And we came up with this 3C framework, which is obviously inspire and like a tribute to the 3Es from Bob Schreiber, as to the mechanisms that we think are largely at play. Obviously, it's a very imperfect framework, because some of the mechanisms could fit a little bit across two or even 3 different Cs. They are difficult to really interpret in a very clean manner. And also there are mechanisms that are so far difficult to attribute to any of those Cs. So it's a simplification. It's something that will provide probably some food for thoughts to individuals who approach the process, and they will have an original idea to build their own investigation, but they will have to stay very cautious because they might find mechanisms that don't fit in any of those, or they might find mechanisms that are actually at the border or the frontiers between many of them. So that was our intent, and it stemmed from what we did in the lab. In the lab, we have studied how cancer cells evade recognition by the immune system in the setting of radiotherapy, and there's a little bit of all of them. There's a little bit of camouflage, as cancer cells not expressing MHC class 1 molecules. There's a little bit of coercion in the sense of reduced apoion interferon secretion, and there's a little bit of cytoprotection through mechanisms like autophagy that are very strong inhibitors of the cytotoxicity of T cells, for instance. So that's where it all came from.
Dr. Lorenzo, além de seus conhecidos efeitos citostáticos, os inibidores de CDK4 e 6 têm sido cada vez mais reconhecidos por sua capacidade de modular a imunidade antitumoral. Você poderia explicar os mecanismos imunoestimulatórios específicos desencadeados por esses agentes e como eles podem ser utilizados para melhorar os resultados da imunoterapia, especialmente em tumores com fenótipo imunoevasivo?
Yes. We have been working with CDK4/6 inhibitors for now more than 6 years, and that all started exactly on those assumptions that you just mentioned, on the idea that these drugs were conceived as cell cycle stoppers. And okay, cancer cells proliferate a lot. Some of them, especially hormone receptor positive breast cancer cells, proliferate a lot because they have a lot of CDK4 and 6 activation. So the idea was, okay, let's inhibit those kinases. Other cell types will not be so dependent on them, and they will be spared by the potential toxicity of the therapy. And those drugs have been proven very, very successful in the clinic of hormone receptor positive breast cancer, as much as now being first-line therapy for advanced metastatic disease. Alongside, so throughout the 2020, the idea came around that those drugs could also drive an immune response. And indeed, in the mouse, there is considerable data suggesting that it happens. There's considerable data suggesting that it happens through a variety of mechanisms, including better exposure of antigens, so better visibility to the immune system, which one could call inhibited camouflage, through a better secretion of cytokines that activate and recruit immune cells that one could call inhibited coercion. And also through the upregulation of some molecules that are involved in the cytotoxicity of T cells, like that receptor that one could call inhibited cytoprotection. The problem with that day, and we really started our investigation in a unique model of hormone receptor positive breast cancer, which is where these drugs are used based on that assumption. But when we ended up in our model trying to figure out if the immune system was involved in the efficacy of the therapy, we understood it was not. So we started to question what was out there in the literature, and on a better digging, we figured out that all the data that was out there came from models that are not really model of an immunoevasive tumor. They're model of tumors that are really immunosensitive, melanoma, renal cell carcinoma, and those tumors are not even treated by this drug in the clinics. So our model in hormone receptor positive breast cancer, and the paper is going to be published hopefully this week. Actually, it's a Nature Cancer paper coming out soon. Demonstrate that these drugs in the hormone receptor positive breast cancer setting, and I'm not talking about other diseases here. In other diseases, they might do different things, but in that disease, they seem to promote an immunosuppressive recruitment of gamma delta T cells that transform local macrophages towards an immunosuppressive phenotype that would limit the activity of the drug themselves. So the bottom line is, sorry, cat in the way. The bottom line is, yeah, these drugs talk to the immune system. They probably have effects that are probably both immunostimulatory and immunosuppressive, but depending on which tumors we are talking about, they might be completely different, and we have to be careful because that's one of the risks of extrapolating data from different models to clinical realities where these drugs are actually used.
Excluindo um tipo específico de radioterapia interna, a radiação deve ser direcionada ao tumor para evitar os efeitos colaterais em células saudáveis. No entanto, em um dos seus artigos, você e seus colegas discutiram o resultado positivo da microbiota irradiada em baixas doses quando combinada com um bloqueio de checkpoint imunológico. Você poderia compartilhar conosco um pouco sobre sua linha de pensamento enquanto trabalhava nesse projeto e quais são suas perspectivas futuras seguindo essa linha de terapia?
This is a very interesting and unexpected to some degree, well, maybe not unexpected, but partially unexpected effect of radiotherapy. And there was indication in the literature that low dose could actually be immunostimulatory in multiple ways and hence drive these immune responses that could help the activity of therapy somewhere else, which is called abscopal response. In this specific case, while in other cases, like in work from Jim Welsh at MD Anderson, the idea of using low dose is more of a way to enable the immune infiltration of lesions that would be not particularly hot, and they would be in a place where using a full dose would be complicated. As you said, we need to spare healthy tissue. Some healthy tissues are really untouchable because if you touch them, you die because of radiation. For instance, the heart. When a tumor is very close to the heart, you can do what you can in terms of dosimetry, but you have to be very, very careful with the heart. So you cannot really push doses too much there because there's always a part of the radiation that will reach the healthy tissue around. Even though it's low, even though with novel technology it's very low, still you cannot take the risk. I have two choices for other lesions that I cannot treat the way. Either I leave them non-irradiated, either I irradiate them a little bit. And that's what he did. And in that case, it was really, let's bring immune cell in, not a different strategy. In the Zitvogel scenario, the idea was largely, it was sort of a coincidental finding, but what turns out to be the case that there's a modulation of the gut microbiome by radiotherapy that now generates an immunostimulatory signal that is capable of boosting a systemic immune response against lesions that are not irradiated. And they are following, they have beautiful clinical data on that, and they are following up on this concept for sure.